Good morning. Hope everyone's doing well. The 4 of you that are here this morning. Well, so hopefully you got my email last night about, there was like some confusion about the last lab. You only had to do the first page, so. Okay, we're gonna finish up the last chapter hopefully today, which is gonna be on acids and bases. This last part is all on calculations. So let me share my screen. So we talked about water can act as either an acid or a base, which means that it's amphoteric. Even if we are in a situation where we're with pure water, so only water molecules, there's a process where water will actually ionize with itself, there's this process of self-ionization where one water molecule will transfer a hydrogen to an adjacent water molecule, producing in a temporary H3O plus and an OH minus. So this self-ionization of water, if we happen to be at 25 degrees Celsius, the concentration of the H3O plus is equal to the concentration of the OH minus. So obviously, if one water molecule is transferring, let's say this water molecule here was transferring its H over to this water molecule, you would get one of these and one of these. So these two things should equal each other in pure water. And each of them will have a concentration of 1.0 times 10 to the negative 7 molarity. So there's this constant, this thing called the Kw constant, which says that if I take the concentration of my H3O plus and I multiply it by my OH minus, it will always equal this value of 1.0 times 10 to the negative 14th. And for pure water, where they got this Kw constant, it's this 1.0 times 10 to the negative 7, which we said that was the concentration of both of these guys, times 1.0 times 10 to the negative 7. These two multiplied by each other will give us this number. Now, the interesting thing about this Kw constant is it doesn't just apply to a water solution. It actually applies, a pure water solution, it applies to any sort of solution. So if I have a solution that's acidic, or I have a solution that's basic, the amount of H3O plus, or the amount of the acid times the amount of the base, is going to equal this number. And I'll show you guys how you can use that equation. In a neutral solution, these two things equal each other. Hold on one second. Gabby? Gabby, please, you need to go see Miss Brittany. I'm working right now. I love you. Sorry, my daughter snuck in. And lock the door. Yeah, Leanna, she's awesome. She's a real piece of work. She's a total mini me for sure. I'm definitely getting all of my transgressions back. Times 2, because I have another daughter as well. Okay, so I'm gonna hop from here real quick over to our whiteboard, because I want to make this square that I find really useful when teaching all these equations. It sort of just explains, consolidates all of the stuff on these last like 20 pages of our slides. So let's go ahead and make a square. And at one point over here, I want you to write H3O plus in brackets. Now the brackets are talking about concentration, okay? So when you see something set in brackets like that, it's saying, what is the concentration? How many like moles per liter? So put that in one corner. in a corner over here, I want you to put the OH minus concentration. Down here in the lower right-hand corner, let's put something called POH, which you might not be super comfortable with. That's okay, we'll go over it. And then in this lower left-hand corner, we'll put pH, which maybe sounds a little bit more familiar for you. So all 4 of these corners will relate to each other. You can't go across though. All right, we can't go like this. And we're gonna fill in our sort of flow chart between each of these corners. So right now we've got this relationship here. The relationship says, and I can go in either direction using this equation, which says that H3O plus times my OH minus will always equal KW. And KW is 1.0 times 10 to the negative 14. If you know anything about the pH scale is on, it's a value of 0 to 14. So that's why that number is there. So if I know one of these, I can solve for the other one, right? Because it always equals this constant. So let's try and do that back on the slides. So I've got these 3 values. We'll do the first one together. So it says calculate the OH concentration for each solution and determine whether the solution is acidic, basic, or neutral. So let's do A together and then I'll have you do the other 2 on your own. So if I know for A here, I've got an H3O plus concentration that is equal to 7.5 times 10 to the negative 5th, big M, molarity is big M. I want to figure out what is my OH. Okay, well, OH, well, I know my KW constant. KW is equal to H3O plus times my OH minus. And remember, H3O plus, this is talking about an acidic thing. This is talking about a basic thing. So I know this thing here. I want to solve for this. So I need to get this by itself. So in order to get this by itself, I'm going to divide this side by the H3O plus concentration. And I'm going to divide this side by the H3O plus concentration. So here is my value. So OH, specifically OH minus, should equal my KW, and that's 1.0 times 10 to the negative 14, divided by whatever my H3O plus concentration is. And so for this first one, it's 7.5 times 10 to the negative 5th. Now, when you're plugging this into your calculator, you want to use parentheses here to separate those, or you want to use the EE value. So like 1 EE negative 14, so that you can couple the exponent with the digit. So when we plug this in, I'm going to turn my phone to the side to get my exponents. 1 EE 14 divided by all right, I ended up with a value of 1.3 times 10 to the negative 10. And whatever the H3O plus exponent is and the OH exponent, those should add up to get relatively close to negative 14. Okay, sometimes they overshoot it or undershoot it just slightly, but it should be within the range of like negative 13 to negative 15. So this is what my OH is equal to. So the problem wants to also know, is it acidic, is it basic, or is it neutral? Well, if this is what my OH is, and remember this is what my H3O plus is. Okay, this is talking about acid This is talking about base. So in order to determine whether the whole solution is acidic, basic, or neutral, you need to see which one of these guys is kind of winning, which one is there's more of it. If these two values were equal to each other, it would be 1.0 times 10 to the negative 7. If they were equal, that would be neutral. In this case, I've got an acidic solution of 7.5 times 10 to the negative 5. That's a bigger number than 1.3 times 10 to the negative 10. It may not seem bigger, but remember, these are negative exponents. So this is saying you move the decimal to the left 5. This is saying you move the decimal to the left 10. This number is getting very, very small, okay? So what we've got here is a situation where the acid is a higher concentration, or not a higher concentration, but or it is a higher concentration, but we've got more of it. Okay, so we've got more acid in our given solution. So the acid wins, so we are acidic. So I'm gonna have you do the other two. It's the same thing. I'll leave this up. You know for each one of these, the H3O plus concentration. So all you do is in this equation right here, just change out whatever that denominator is, all right, for the other values. So I'll give you all 3 minutes to work on that, and we'll go back and look at it. Also determine if it's acidic, basic, or neutral. Okay, so instead of having to deal with my horrible handwriting for all of these, we will just pull up how they did it. So this was the A that we did. So in B, same setup. You take your 1.0 times 10 to the negative 14th, you divide it by the 1.5 times 10 to the negative 9th, and you should end up with 6.7 times 10 to the negative 6. So looking at this value versus your H3O plus value, which was this thing here, well, this is a bigger number than this. So in this case, the basic material wins out. The last one, we got an H3O plus concentration of 1.0 times 10 to the negative 7th, and we got an OH concentration of 1.0 times 10 to the negative 7th. So these two things equal each other. When they equal each other, this is a neutral solution. So it kind of explains what we've already learned, but when these two things equal each other in a neutral solution, they'll both be 1.0 times 10 to the negative 7. In an acidic solution, your H3O plus solution, the value will be greater than that 1.0. That's kind of the cutoff point. That's the middle line. If we're both on that, we're neutral. If one is higher than that, it wins, it's acidic. If it's lower than that, it loses, it's basic. So as far as this H3O plus and OH concentration, right, as we increase the concentration of H3O plus, we become more acidic. As we decrease the concentration of OH, we become more acidic, and vice versa. As we decrease acid and we increase base, we become more basic. So pH and POH scales, specifically pH, you're probably more comfortable with, are just ways to express acidity and basicity. So when looking at a pH scale, pH, the big H is talking about your H pluses or your H3O pluses, right? It's talking about how much acid do you have. So in a pH solution, 7 is neutral. As the number gets lower, you become more acidic. You have a higher acidic concentration. As your number gets higher, you become more basic. So if I said something has a pH of 3.2, that would be acidic. If I said it had a pH of 11, that would be basic. A pH of 7, right in the middle. So the pH scale is actually what we call a logarithmic scale. A decrease in 1 unit on the pH scale corresponds to an increase in H3O concentration by a factor of 10. So if I go from 4, a pH of 4 to a pH of 3, we're increasing our acidity. We're increasing by a factor of 10, or it's going from 10 to the negative 4 to 10 to the negative 3. So a 10 jump. That means that if I go from 3 to 2, I'm not increasing just by a factor of 10, but then I'm actually increasing from originally from 4, that's a factor of 100, or 10 and then 10 here, 10 of these to give us 100. So it's a logarithmic scale. Oh, awesome. So it doesn't give us the equation. So here's the equation. So let's go back to our square so we can fill in some of these other limbs. All right, so the relationship between pH and H3O plus. So if I know my H3O plus and I want to calculate pH, let's say we're going to go this way. So don't mix these two up. So I know this and I want to find this. That is pH will equal the negative log of the H3O plus. If you're wondering what's log, it's a function on your calculator. Log is like the opposite of 10 to the. So you know how like multiplication is the opposite of division, addition is the opposite of subtraction. Well, when you say like 10 to the third power, the opposite of that or to undo that would be the log value. So you need to make sure that you plug it into the calculator, negative log, and then the H3O concentration. Let's just do the same thing over here. So this equation is very similar. If I happen to know my OH and I want to get my POH, POH is equal to the negative log, but of the OH concentration. Okay, so where pH talks about how much H3O plus you have or how much acid you have, POH talks about how much OH minus or how much base you have. So let's try this thing out here on these slides. So calculate the pH of each solution and indicate whether it's acidic or basic. So looking at this right here, I can already tell that this thing is acidic. I don't even need to convert it to pH because looking at this 1.8 times 10 to the negative 4, that's a bigger concentration than 1.0 times 10 to the negative 7, but let's do it anyway. And we need to know the pH. So in order to calculate pH, pH is going to equal the negative log of your H3O plus concentration, or it's going to be equal to the negative log of 1.8 times 10 to the negative 4. So I want you to actually manually plug that into your calculator. I don't want you to just have me plug it in. I want you to do it because if for some reason you're getting a funky answer that isn't matching ours, I want to clear that up now. So I'm using my phone calculator. I got to kind of plug it in backwards. I have to plug in the 1.8 to the negative 4, and then I have to hit the log button. If you're using a scientific calculator, you can just type it in like you would, like how it's written there. So when I did this, I got 3.7, a pH of 3.7. Don't forget the negative. If you don't put the negative in, your number will be negative. You'll have negative pH. So 3.7 on the pH scale is totally acidic. All right, I want you to do the same thing for B. I'll give you just, 2 minutes. Gabrielle asks, how did I type it into my phone? Okay, so if you have an iPhone, are you using an iPhone calculator, Gabriella? Yes, okay. So turn it to the side so you've got the expanded version. Now, this is why a scientific calculator is more beneficial because you can just plug it in the way that it's written here. But when I plug this into my calculator, first I have to plug this thing in. All right, so I hit 1.8 and then I hit the EE button, EE4, and you'll see when the 4 pops up, it's a positive, so I need to throw a negative in front of it. So I hit the negative button. So and then I hit equal to make sure that it's gotten that. So now I have 0.00018. If that doesn't work for you, you don't like to do it that way, you can just type in 1.8 times 10 to the negative 4. You can do it that way as well, okay? So now that you've gotten this number in your calculator, or the 0.00018, or in whatever fashion you can get that into your calculator, now hit the log button, and you'll see that it says negative 3.74. And then you take the negative of that. I don't actually manually plug the negative in because I know I just am going to flip the sign. All right, Gabrielle, if that didn't make sense, or you need a little bit more with that, we can talk after class and I can try and help you plug that in. Okay, but with the calculator, with your iPhone calculator, you first have to plug this in. Then you hit the log button. That worked? Okay, good. Okay, so let's look at, they've got it written out so that you don't have to see my excruciating handwriting. So they had the pH equals the negative log of whatever your H3O plus concentration is. In this case, our H3O plus concentration is much smaller than the last one, right? This was 10 to the negative 4. This is 10 to the negative 9. That's tiny. And it's tinier than that negative 7 cutoff. So I know that this is going to be a basic solution, but let's plug it in to make sure. So we hit the negative log of the 7.2 times 10 to the negative 9. Again, if you have your iPhone, you'll plug this in and then hit the log button. And then we get a negative 8.14 or 8.14. That is bigger than 7, so that means that this is a basic solution. We can go the other direction as well. So you can get the H3O plus concentration from the pH. And I will show you how to do that. Let's add that lim first to our square here. So we can go in the other direction as well. There to there. If I know pH, then I can solve for my H3O or my OH concentration. I'm going to divert just for a minute to do a little bit of math because I find that some people appreciate knowing where these equations, how you can derive them from each other. So I'm just going to show you real quick. If this is like over your head or you just can't stand the math, don't worry about it. Just memorize the square. So if we know that pH equals the negative log of H3O plus. Well, let's say I want to solve for this thing here because I know my pH, but I don't know this. Then I need to sort of turn this equation inside out, right? So I have to move these things to the other side. So how do I do that? Well, if there's a negative here, I'm going to multiply this side by a negative 1, right? That'll get rid of the negative. And then I multiply this side by a negative 1. So what ends up happening is the negative disappears and the negative has moved to the other side. So we've got negative pH equals the log of the H3O plus. Now I want to get this by itself. I can't divide by log. That's not what's happening here. This isn't a multiplication division. Log, remember, is the opposite of your 10 to the exponent. So in order to get rid of this thing, I have to do that. So I have to go and take both sides and say 10 to those numbers, 10 to those numbers. So then the 10 and the log will cancel out and this stays preserved. So now I know that my H3O plus is equal to 10 to the negative pH. Okay, you take 10 and then you carry it up to whatever your pH is in the negative. So that's where that equation, this equation is coming from. If you're like, I don't know that, that's okay. Just write it down somewhere. So let's put this in here. If I know pH and I want to get H3O plus, well, H3O plus is equal to 10 to the negative pH. Same thing with this. Say I know POH and I want to find the OH concentration. It's a mirror image of this. We just plug in OH stuff though. So OH concentration is equal to the negative, or I'm sorry, 10 to the negative POH. Oh, squeeze it in there. We can get it. Okay. So this goes here. This goes here. I just am going to finish this off. pH and POH. How do these things relate to each other? Super simple equation. I really like this one. This one is like a little more work because I got to use like exponents and stuff. This one's so easy. pH plus POH always equals 14. So if you know your pH, you can find your POH by subtracting it from 14 and vice versa. So this is super easy. Again, remember, there is no way to go crisscross. Okay, so if I gave you something like H3O plus and I wanted to know the POH, you'd have to do a two-stepper. You'd have to either use this to get to this and then drop down, or I would prefer to use this and then cross over because anytime I can use this versus the KW constant, I do. So there's our nifty square. Let's practice a little bit with this reverse of our previous equation. Okay, so calculate the H3O plus concentration for a solution with a pH of 4.8. So we know pH is equal to 4.80. We want to find, so given we're trying to find H3O plus. Well, I know that H3O plus equals 10 to the negative pH. So I literally just plug it in, 10 to the negative 4.180. It's not enough to leave it like this. You need to actually run it through your calculator. So go ahead and do that. So you'll take this is another situation. So if you're plugging this into a scientific calculator, just plug it in the way you got it. If you're using your phone calculator, you first have to plug in the exponent and then hit the little 10 to the x button. Okay, so when I'm running through this, I'll type in 4.80, I'll flip it to a negative, and then I hit that 10x button. And I end up with a decimal. Please write it as a scientific notation. So 1.58 times 10 to the negative 1, 2, 3, 4, 5, negative 5. Okay, and this is big M molarity. Questions on that? Don't worry, I'm gonna pull up their stuff here. So here is all those equations sort of clumped together. You can memorize these. I think the square is helpful. All right. So let's play around with these a little bit. So using your square, some space here. Okay, so you're given an OH minus concentration of 1.7 times 10 to the negative fifth molarity. I want you to find two things. A, I want you to find the POH. And then in B, I want you to find the pH. And then I want you to tell me if it's acidic, basic, so let's see, acidic, basic, or neutral. I'll give you 3 minutes for that. Obviously, if you have a question while you're working on it, let me know. Okay, so this is kind of a two-step problem that I've like guided you through the steps. So let's do this one, and then the next one I'll just throw it all together. All right. So we know our OH concentration, and we want to figure out POH. So OH, POH, we're going to use our equation that relates those two. POH is going to equal the negative log of our OH concentration, which is the negative log of this thing right here. 1.7 times 10 to the negative fifth. So plugging that in. Hold on 1 second. Okay. So I get a POH equal to 4.77. Now, when you're looking at this, remember you're talking about POH, which is like the inverse of pH. So if I see 4.77 on the POH scale, that's not acidic. That's actually basic because the POH is a flip. So when asking acidic, basic, or neutral, I wouldn't look at this and say, oh, it's acidic because it's lower than 7. I have to convert it to pH or mentally know it's the opposite. So pH is going to be equal to 14 minus my POH, which is the 4.77. And I end up getting a pH of 9.23. That now, once I'm in pH scale, the 9.23, well, if it's a higher number, that's basic. Okay, so it's the opposite for POH. pH low numbers are acidic, POH low numbers are basic. I'm going to give you another one. Let's say we've got what is the POH of a 3.6 times 10 to the negative 8 molar HCl solution. Okay, so what is the POH of a 3.6 times 10 to the negative 8 molar HCl solution? Don't be freaked out by seeing this. HCl is a strong acid. When it's a strong acid, it means that every H plus and every Cl will be ionized. So whatever the concentration of the whole molecule is, it's the same as the concentration of the H, right? So you can just use this as your H plus concentration or your H3O plus. Remember, those two things are saying the same thing. All right, so I'll give you a minute to work through that one. Well, I'll give you 3 minutes to work through that one. Okay, so we know something about the H plus concentration or the H3O plus concentration. This is an acid and it's a strong acid, so it's full dissociation. We want to find the POH. So let's go up to our square. Just to talk about our thought process. So we know this. We want to find this. There's no way to cross. I've got to go through a two-stepper. If you want to go this way, H3O plus to OH minus, do it, and then drop down. I don't like using this because I don't like plugging all the exponents into my calculator because I'm lazy. This is so much easier. So I'm going to go this way. All right. But if you were to have gone this way, it would give you the same answer. I'm going to drop this way. All right. So I'm going to go down to pH and then cut over. So plugging this in, I've got I'm going to go H3O plus to pH and then pH to POH. So pH is going to equal the negative log of my H3O plus, and in this case, it's 3.6 times 10 to the negative 8. So don't get freaked out if you see it written as a material, like as a molecule. You just assume that it's a 1-to-1. If you had two H's for this, you would have to double that number, but I don't think you'll see anything like that. You may see it on the homework, you won't see it on the test. So for this one, let's see what our pH is. So all right, so I got a pH of negative, no, not negative, 7.44. I want to figure out POH. So POH is going to equal 14 minus that, minus 7.44. I end up with a POH of 6.56. These are pretty close to each other. It's almost a neutral solution, but the base is a little stronger. Yeah, it's a little bit more basic. Another way you could see that 3.6 times 10 to the negative 8. This is smaller than that 1.0 times 10 to the negative 7. Remember, this is the cutoff. This 1.0 times 10 to the negative 7. That's sort of our neutral cutoff. Any questions on that? On using the square to calculate any of these values? How you can go around? Okay. Then we will move to the very final part of this, which is just talking about a buffer solution. So a buffer solution is a solution that will resist pH change. So your blood is a good example of a buffer solution. If I was to add acid to your blood, it would neutralize it so that the pH wouldn't change. Same thing if I added base, it would neutralize it so the pH wouldn't change. Buffers contain a Bronsted-Lowry weak acid and its conjugate base. The weak acid will neutralize any added base. The conjugate base will neutralize any acid. So both of them are existing at the same time so that they can neutralize either an addition of acid or base. So here is human blood. Blood pH likes to be between 7.36 and 7.4. That's a pretty narrow pH window. And if you go outside of that, like if your pH drops below 7, that's not very far from this, or above 7.8, not very far from this, you would die. So our blood is a very effective pH buffer solution, actually. Here's an example of a buffer solution. We've got this thing here. So our acetic acid. Acetic acid is a weak acid. It has to be a weak acid. If it's a strong acid, it can't create a buffer solution. It'll just form an acidic solution. So we've got some of this weak acid existing and some of this conjugate base existing. If I was to add base, the acid would eat it up, neutralize it. If I add acid, the conjugate base will eat it up and form a salt to neutralize. So again, a buffer solution contains a significant amount of a weak acid and its conjugate base. That's what makes like a really good buffer solution. And that's it. That's it. We're done. You are done learning chemistry for the semester. Well, you're done learning new chemistry for the semester. Now you just have to understand it all for the final. So let's take a quick peek at the syllabus while we're here, just so we can talk about the last couple days of the semester because we're almost done. So as far as what our next week and a half looks like, oh, come on. There we go. All right, so we're sitting here. We had done a little bit of acid bases early, so we finished that up early. Your final test is going to be this Sunday. So that's going to cover chapter 11, 13, and 14. That's gases, solutions, and acids and bases. So make sure to get that done on Sunday or Monday. The final exam, it says that it's set over here, but it's actually going to be due, I'm going to make it for the 17th and the 18th, all right, which is, I believe that Thursday, Friday. So you'll have Thursday, Friday to take it. We will have an opportunity to do a final review on Wednesday. So we are meeting on Wednesday, but that's really for you. So I want you to bring questions. If you want to review stuff for this fourth test, we can do that. If you want to go beyond what we're doing for this fourth test, though, please bring questions on anything from the semester. So if you want, and I recommend it, go through and say, oh, nomenclature. I do not know how to name acids and bases, or chemical bonding. Those Lewis-Dot structures are killing me. And, it can be that. It doesn't have to be a specific question. It can be like a general idea of, I don't get this. And I will come up with some example problems that we can go over, okay? We won't meet on Monday of next week. Unless there's a desire for it beyond this review, we'll just have the final. All labs, if you have anything late, you want to get a point here or there, it needs to be turned in by that Sunday. Okay. Any questions for my few people that are here today on what the rest of the semester looks like? No? You're all good? Okay, well then we're gonna call it today. Call it early. You guys worked so hard for the whole semester. You get out 15 minutes early today. If you do have a private question, feel free to stay around. Otherwise, I will hopefully I'll see you guys on Wednesday. Please meet, because the review can be really helpful. Sometimes it is just way easier